Hey guys, I'm gonna be going over a physics 2 problem, and in this problem you can see that a very thin plastic rod right here, and then you have an observation point, and we want to calculate what the delta Q would be for the first part. So for any arbitrary length on the rod, you want to calculate the delta Q of that. So for this part, it's just delta Q is equal to some delta X, so some arbitrary length on a rod over the whole thing. So in this case, the whole thing is L. And this is a very thin rod, so you don't need to account for the area, so just L. And then times that by the whole charge, which is negative Q. And that's all for the first part. Okay, so for the second part of this problem, it's asking to draw a relative position vector. So from R observation minus R source, which is the same thing as the vector source to the observation, because that's how you calculate R vector. So I've drawn sketch here, and so let's say here's some arbitrary point, and then all it is from a vector pointing to the observation location, and that's R observation minus R source right here. And then the question also asks for the direction of the electric field. So in this case, since there's a negative Q charge on the rod, so due to this point, the electric field will go in this direction. So that's E vector. And that's it for part B. Alright. So for part C, it's asking us to derive an expression for the vector field delta E of the slice of the rod at the observation location marked X. So here, the observation location, you can tell, is the length of the rod plus this A value, which we don't know. So that's the L plus A is the X, because that's just all of the X. And then the Y component is B. So the observation location is at a vector L plus A for the X component, B for the Y component, and there's no Z component, so 0. And then minus the source, which is a arbitrary point, so anywhere on the rod on the x-axis, so it's just X, because we don't know where it is, so we just denote it as X. And then there's no Y component in this problem, and there's no Z component. So this is your R vector. So R vector is equal to L plus A minus X for the X component, B for the Y component, and 0 for the Z component. So that is our vector. Now you have to also find our magnitude, which is just you have to square all of these components and take the square root of it. So R mag is equal to the square root of L plus A minus X squared plus B squared, and that's R mag. So the next important part is r hat, which is the unit vector in this case. So maybe you know just the r vector. So this divided by r mag, which is this. So it's just L plus A minus X B 0 divided by the square root of L plus A minus X squared plus B squared. So that's your R vec. Now recall that the electric field delta E is just Coulomb's law, so 1 over 4 pi epsilon naught. In this case, instead of just normal Q, it's just delta Q because we're just finding the influence from that arbitrary location. So delta Q divided by the magnitude R vector squared. So we already found the magnitude earlier, which is this thing right here. And then times the unit vector. So in this case, the unit vector is all of this. So L plus A minus X B 0 divided by now you can tell right here where you could put in the R, the magnitude that we got from earlier, which is up here. So if you square that, you can just plug that in as this right here is just L plus A, whoops, L plus A minus X squared plus B squared by itself, since the squared got rid of the square root right here. So that's that. And the delta Q, recall that in part A we solved for that. So here we just plug in what we got for delta Q earlier, which was delta X over L times negative Q. So this right here is delta X over L times negative Q. So so the final answer is delta E is equal to 1 over 4 pi epsilon naught times delta X over L times negative Q over, see the bottom here, this times this is equal to like the inside to the 3/2, and that's just an exponential rule that you should know. When you multiply exponents, they just add. So this is technically to the 1/2, so plus to the 1 plus 1. This is technically exponent to the 1, so 1/2 plus 1 is 3/2. So L plus A minus X squared plus B squared, all this to 3/2, and then times the unit vector without the bottom part. So L plus A minus X B 0, and this is your answer for this part. Alright, so for this part, you just want to see the integral required to determine the electric field at the observation location X. So like from the whole rod, what will the electric field be? So for this, you take an integral because you want to see the contribution from every delta X technically. So for this, we want to take an integral. So this is fairly simple. So pretty much what you do is you have your delta E from before, but now you want to take the integral of it. The important thing to remember here is that when you take an integral, you want to see where you're trying to integrate from, the integrating factors. So in this case, the rod goes from 0 to the length of L. And your integrating factor right here is x, because you're trying to like calculate it on each thing on the x-axis. So in this case, it would be from 0 to L. 0 to L. And everything else pretty much remains the same. So 1 over 4 pi epsilon naught negative q over L. In this case, it's going to be dx, because delta x from earlier will turn into dx, since that is the integrating factor that you are integrating about. Everything else pretty much remains the same. So I'm pretty much just rewriting what we calculated earlier for delta E at any arbitrary point. The only difference now that you have you're integrating instead. And that's pretty much it.